All right, so this was this constants page here. We had our ionic compound solubility. Hold for dramatic effect. Hopefully, maybe. Okay. We have our solubility of gases, Henry's law. So there are some formulas on here. And again, I sort of make note here of what it is that you're expected to know concentration-wise and what you'll be given concentration-wise. All right? And importantly, our colligative properties. We have this chart here that we used, and we have our colligative property formulas as well. Okay? Cool. So now we're going to sort of pivot away from solutions, and we're going to start talking about what is my favorite topic in Chemistry 1B. This is chapter 13 on equilibria. All right, and before we sort of dive in and explain what exactly we're talking about here, let me just note that this is going to be something that we sort of lay some groundwork here. We're going to introduce this particular problem-solving strategy, and then we're going to use it over and over and over again to talk about chemical reactions. All right? So for example, we're going to introduce equilibrium here today, and then next chapter is on acids and bases. And everything we discuss with acids and bases are these equilibrium problems, just within that context of that specific reaction. Okay? So what we're doing is kind of laying some groundwork, building the tools in our tool chest, and then we'll apply that to different categories of reactions as we go forward. Okay, so what are we talking about here? So we're going to start with kind of just a generic reaction here where we have our reactant A and it gets converted into product B. All right, so here is our chemical equation. Again, A is going to be our reactant, and B is going to be our product. All right, and what we're going to do is we're going to study this reaction, okay, as a function of time. So we're going to create this little graph here, where on our x-axis we're measuring time, and on our y-axis we have our concentration. Chemists have a lot of different strategies for how we can go about measuring concentrations, but monitoring the concentration of things is something we do all the time. We got a bunch of different tricks. It sort of depends on exactly what our reactant or product is, but we can do this. Any scientist would be able to monitor concentrations over time here. All right? And what we're going to do is we're going to combine only our reactant into this flask. So at time t equals 0, we don't have any product. All right? So then I'm going to start the clock here. I'm going to kick things off. What's going to happen to the concentration of my reactant A as time goes on? Is it going to increase or decrease? It's going to decrease. And it's going to decrease because my reactant A is getting converted into that product B. So my product B's concentration is going to increase as a function of time. All right, so far nothing crazy. But this is sort of where we're going to update our way of thinking about these chemical reactions here. So up until now, you've always kind of thought of reactions as all of your reactant gets converted to product. And that is true for some reactions. A combustion reaction, for example, that's taking place in your car engine is an incredibly efficient reaction that always goes 100% to completion. 100% of that gasoline gets combusted into carbon dioxide and water. But there are plenty of other reactions out there that do not go all the way to completion. Even if you gave them 1,000,000 years, you let this thing sit here for forever, it still wouldn't go all the way to completion, meaning that as a function of time, at some point I'm going to reach this time where my concentration of A is no longer changing, but it's also not 0, right? I still have A left over in that flask. And likewise, my concentration of B, it increases as a function of time. But again, it's going to plateau here before it reaches that full 100% completion level. All right? So this idea about chemical reactions always just going from reactant to product and going 100% to completion is not true. Okay? So first of all, this region here, where our concentrations are no longer changing as a function of time, this is what we call equilibrium. All right, so we're going to make some notes about equilibrium here. All right, so importantly, all reactions will proceed towards their equilibrium. All right, and as we've noted on our little graph here, at equilibrium, the concentration of reactants and products are no longer changing, all right, or remain constant. Okay, does not change, remains constant. Okay, so all reactions are going to proceed towards this place we call equilibrium, which is when the concentration of reactants and products is no longer changing in that mixture that you have, in your little flask where your reaction is taking place. Okay? Now, here's the crazy thing about equilibrium, and again, the way that we have to update our thinking about chemical reactions compared to general chemistry, is we have this reaction. We have A being converted to B, right? That's happening. Our concentration of B is increasing. Our concentration of A is decreasing. But then they reach this equilibrium here, and it's not like all the molecules get together and say, hey guys, all right, let's stop reacting. We're done here. That was fun, all right? That's not what happens. It's not like everybody decides no more reaction happens. It's just that reactions are always happening in both directions at the same time. So yes, we have A being converted into B, but we also have B being converted back into A. This reaction is going in both directions at the same time, and so when you reach equilibrium here, it's not that no more reaction is occurring, it's just that the rate of that forward reaction, the amount of A being converted to B, is now equal to the rate of the reversed reaction, right? The amount of B being converted back into A, and that's why our concentrations are no longer changing. If you were to pick a molecule and stare at it, it would be converted from reactant back to product, or from reactant to product, then back to reactant again, then to product again, over and over and over again. Okay, so this reaction is still constantly going on. It's just we use, first of all, for reactions that are like this, where they have this sort of, they don't go all the way to completion. We don't use that one direction arrow that you're used to seeing. We use this equilibrium arrow here. All right, so this specifically represents a reaction that has that dynamic equilibrium. And we would say A being converted into B, this is our forward reaction. But again, B gets converted back into A, our reverse reaction. Okay, and so at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. All right. Cool. So we have this like quantitative measure of our equilibrium. what we're going to spend a lot of time today talking about our equilibrium constant. All right, equilibrium constants have this symbol that we use, uppercase K. All right, and your equilibrium constant is a value, so every reaction has an equilibrium constant. You can go look it up in one of those big books that they have. All right, and what that tells you, all right, so your equilibrium constant tells you which side of your reaction, by that I mean reactants or products, is favored at equilibrium. Okay? We're going to kind of keep it simple now, looking at this equilibrium constant while we talk about it, and then we'll introduce like a real chemical reaction and talk about building our equilibrium expression for that. But the most important thing to remember about your equilibrium constants, what I still chant to myself every time I build one of these equilibrium expressions, is it's the concentration of product over the concentration of reactant. All right? And that's specifically at equilibrium. Okay, and the magical thing about this equilibrium constant, about this number, is that it is true, it is a constant value for a given reaction, regardless of how much reactant or product you started with, right? Your reaction's always going to proceed towards equilibrium. I could have started out with 1 mole or 100 moles. At the end, when it reaches equilibrium, if I take the concentration of my product divided by the concentration of reactant, I'll get that same number, that same constant value every single time, all right? So again, this value is going to tell you whether or not your reaction favors your products or your reactants at equilibrium. And let's think about it. If K is a big number, what does that mean? I'm going to have more product or reactant at equilibrium? Yeah, why product? Because that's what's in my numerator here. All right, so a big number for K is a reaction that favors your products. If you have a little teeny tiny number for your value of K, that means that your numerator is small and that your denominator has to be big. So that would be a reaction that favors your reactants. Okay? So we have these like cutoff values that we use. So again, greater than 1 favors the products, less than 1 favors the reactants. But we go a little bit further, all right? We say that if K has a value, so let's just mark this, our values for K, our value cutoffs. All right, if K is a super big number, all right, and the sort of cutoff that we use is 1,000, 10 to the 3. We would say that this reaction strongly favors the products. Right? You're going to have over 1,000 times more product molecules than reactant molecules at equilibrium. So this one would strongly favor the products. This would be a reaction where we would comfortably sort of just say A goes to B. We wouldn't worry about using our equilibrium arrows, right? A reaction that we basically can just assume goes all the way to completion because it strongly favors those products. All right, if K is larger than 1, it's still going to favor those products. All right, but if it's less than that 1,000 cutoff, we say that this is a reaction that only weakly favors our products. this is when we would want to make sure to use that double-headed arrow, right? Our equilibrium arrow. Because you're still going to have an appreciable amount of reactant left over, right? You'll have more product than reactant, but you still got quite a bit of reactant floating around in there. So this would be an example, the little graph that we did at the beginning, this would be an example that would weakly favor the products. Yes, I produced quite a bit of product, but I also still have quite a bit of reactant left over. If K is less than 1, now all of a sudden I have more reactants at equilibrium. But again, we have this cutoff that we use now 1,000th or 10 to the negative 3. This is a reaction that weakly favors the reactants. And again, if we were going to show this reaction here using those, using our chemical equation, we would want to use those double-headed arrows. All right, we call this our dynamic equilibrium range, where we still have, or rather we'll have an appreciable amount of both reactant and product at equilibrium. And then where am I going with this? If K is less than that 10 to the negative 3 cutoff, what do we think we'd say? Now we strongly favor which side? Our reactants. All right. We would probably say that this reaction is going to go strongly in that reverse direction, which basically means you mix these two reactants together, nothing's going to happen. You're not going to create any products. All right? Cool, so these are these values of K. And again, these values tell you something about your reaction. So for every chemical reaction, you can go and look up in one of those big books, or probably nowadays more likely a database somewhere, figure out what the equilibrium constant is for your given reaction. And that tells you something about which side your reactants or products are favored at equilibrium. All right? So how do we build these equilibrium? We said products over reactants. That's going to be our first step here. But let's do an example with an actual chemical reaction and build what we call our equilibrium expressions. All right, there's going to be this function, this equation, that relates our equilibrium constant to our reactant and product concentration. Okay, so let's get a chemical equation going on here. We're going to look at how nitrogen dioxide gas gets converted, and we're going to be good and use our double-headed arrows here since we're talking about equilibrium, to dinitrogen tetraoxide gas. All right, so first step, what's wrong with this chemical equation? It's not balanced. All right, everybody take a second. Balance this chemical equation for me. You can't do anything with it until it's balanced. All right? Just like we couldn't do any stoichiometry without a balanced chemical equation, we can't do any equilibrium without a balanced chemical equation. All right, nothing too crazy here. We're going to need 2 molecules of nitrogen dioxide to react to form 1 molecule of our dinitrogen tetraoxide. Okay, and what we're doing is we're building this equation, all right, this expression that relates that equilibrium constant K to our concentration of our reactants and our products. All right, so step one, all right, let's just header this now, building our equilibrium expression. All right, step one, first thing I chant to myself, products over reactants. So we're going to take our product, that dinitrogen tetraoxide, the concentration of our product over the concentration of our reactant. All right, so step one, products over reactants. Okay, step two, we're going to see these coefficients from our balanced chemical equation appear in our equilibrium expression. But importantly, these coefficients will become exponents in our equilibrium expression. So I have a 2 out front of my reactant concentration. I'm going to then square my reactant constant. I'm sorry, I have 2 out front of my reactant in my balanced chemical equation. So I'm going to square my reactant concentration in my equilibrium expression. So products over reactants are coefficients become exponents. All right, I'm going to add one more rule here when we do some other examples, but for this particular one, that's it. That's your equilibrium expression. So again, when you do this reaction, it doesn't matter how much nitrogen dioxide you start out with. Once that reaction reaches equilibrium, if you take your concentration of product and divide it by your concentration of reactant squared, you're always going to get the same value. All right? It turns out for this particular chemical equation, I looked it up before we got here, this is an equilibrium constant of 6.9. So then what would we say about this particular reaction? Does it favor our reactants or products? Greater than 1, so it favors our products. Does it strongly favor our products or only weakly favor our products? Weakly favors our products, right? It's less than that 10 to the 3 cutoff. Greater than 1, but less than that 10 to the 3 cutoff, so this weakly favors our products. What's up?
I'm just a little bit confused on how you got the like 6.9.
Oh, I looked it up in a book.
Okay.
I don't know that you don't know equilibrium constants just by looking at a chemical equation. I went to one of those big old books and I looked it up for this specific reaction because it's going to be unique to every reaction. So you got to look up your specific reaction, and that's how I got that 6.9 value. Okay? Cool. Since this is a equilibrium constant in terms of concentration, we would call this a Kc. All right, it turns out for gaseous reactions, pressure is directly proportional to concentration, and sometimes it's much easier for gases to measure the pressure of those gases rather than the concentration. And so for gaseous reactions, so let's just note this is C for concentration. For gaseous reactions, you might find it more convenient to talk in terms of a Kp, where now we're going to talk about the amount of reactant and product in terms of the pressure or partial pressure of that gas. But you build it the exact same way. It's still products over reactants. So now it would be the pressure of that product over the pressure of that reactant. And you still turn that coefficient into an exponent. All right, it's just a convenient little trick since concentration and partial pressures are always proportional to one another. All right, so I'm going to have you build one on your own here. All right, we're going to take nitrogen, combine it with hydrogen. Both of these are gases. And we're going to get ammonia, NH3. Okay? You're going to build me our KC for this reaction. Now, since you have two reactants, all right, importantly, I guess let me start you off on this one here. You're going to do our concentration of product divided by our concentration of reactant. Equilibrium expressions are always just multiplication division. So I'm not going to add these two together. I'm going to multiply the concentration of nitrogen times the concentration of hydrogen. All right, so finish this off for me. I did not balance this chemical equation, all right? So go ahead and balance this chemical equation so that you can complete our equilibrium expression here. All right, so I got 2 nitrogens, so I'm going to have to double my product over here. That'll give me a total of 6 hydrogens on this side, meaning I need 3 of those diatomic hydrogen gas molecules. So in my balanced, or rather in my equilibrium expression, my exponent, the 2 in front of my product, means I need to square that product concentration. And my coefficient of 3 out front of my hydrogen gas means I need to cube that hydrogen gas concentration. Cool? Nothing too crazy. All right, and then again, for this one, I went and I looked up in that database the equilibrium constant for this reaction here, and it was 6 times 10 to the 5. So what would I say about this particular reaction? Strongly favors our products. Awesome.
Will we be doing this on our exam?
Yes.
Will we have like the chart? Like, do we have to know the end number?
No, you do not have to have numbers memorized. And we'll sort of graduate to doing more math with these expressions here. But no, you'd always be given an equilibrium constant or some sort of a table that you looked it up on or something like that. Yeah, these are just kind of instructive things so that we can practice our favors reactants products business.
So like we'll just be responsible for like the setting it up.
Correct. So given a unbalanced chemical equation, you should be able to construct me that equilibrium expression. Cool. All right, another one. These reactions tend to be really strongly favoring the products. All right, let's do calcium nitrate. These are now aqueous. Oh, nitrate, I need 2 of them. We combine that with sodium fluoride. Also aqueous. We get these precipitation reactions. All right, where we form solid calcium fluoride and aqueous sodium nitrate. All right, right? My previous example, I could have asked you for either a Kc or a Kp because it was all gaseous. Down here, what are we going to have to use? We're going to have to use a Kc, right? There's no such thing as a pressure of an aqueous solution. All right, but we're going to update our rules for building our equilibrium constants real quick, okay? What we don't have in our equilibrium constants are things we're talking about. Concentration doesn't really make sense. You can't really talk about the concentration of a solid, all right? Likewise, if it was a pure liquid, you don't really talk about concentrations of those pure liquids. So in our equilibrium expression here, if it's anything other than aqueous or gas, we just completely omit it from our equilibrium expression, all right? So we're going to omit any solids or pure liquids. Solids would have that S designation. Our pure liquids have that L designation in our balanced chemical equation. Okay? So in this reaction here, what's not going to appear in my equilibrium expression at all? That calcium fluoride, right? That's just not going to appear in that equilibrium expression at all. These equilibrium values turn out to be completely independent of the amount of calcium fluoride that's in that reaction mixture. All right? So take a second, balance this chemical equation, give me my equilibrium expression.
If the solid isn't going to be in the final thing, do we still have to balance it?
Well, you do need to, it might influence, say, what goes out front here. And that would appear in your equilibrium expression. All right, so I'm going to do my product. Well, so I guess I got to balance it first, right? So I need 2 of these and 2 of these. So I'm going to do my products over my reactants, but again, I'm not going to include that calcium fluoride at all. So I'm just going to have that other product, my sodium nitrate, over my reactants, my calcium nitrate, and my sodium fluoride. So I got my products over my reactants. I've omitted that solid, and I'm going to convert these coefficients into exponents. So I got to square my sodium fluoride concentration and square my sodium nitrate concentration. Okay? So building these equilibrium expressions, products over reactants, our coefficients become exponents, and we omit any solids or liquids from our chemical equation. From our equilibrium expression, sorry. All right. So let's try to use these equilibrium expressions now. Okay, we're going to combine 1.6 molar. Oh, sorry. We're going to use that. We already balanced it and built our equilibrium expression. So we're going to do an example using this particular reaction here. I lied. Let's go for a new one. Just for the sake of practice, let's do hydrogen gas combines with iodine gas to produce hydrogen iodide. And since this is a gaseous reaction, let's go for a Kp here. All right, so since it's a Kp, we're going to define in terms of pressure. My hydrogen iodide, oh, I got to balance. Pressure of my product over the pressure of my reactants. And that coefficient becomes an exponent. So I'm going to have to square my product pressure in my equilibrium expression. Okay. So now let's try to use this one here. All right. We're going to combine 1.5 atm of hydrogen and 2.3 atm of iodine. They are going to react together to form our product, hydrogen iodide. And I'm going to tell you that at equilibrium, the pressure of that hydrogen is now equal to 0.25, let's just keep our safe fit, well, screw it, ATM. All right. So, a few things that I could ask you here. First, what is the pressure of the product at equilibrium? How much product did we make? All right, I could also ask you, what is the value of Kp? All right. So how am I supposed to go about this? I'm telling you how much hydrogen gas we start with and how much iodine gas we start with. And then I'm telling you that at equilibrium, we have 0.25 atm of that hydrogen left over. All right, so how much hydrogen actually reacted here? I start out with 1.5. I have 0.25 left at equilibrium. All right, so the difference is going to be how much reacted. All right, so all of these values are tightly tied together. That's what a balanced chemical equation is doing for us, right? For every hydrogen gas molecule that reacted, there was exactly one iodine molecule that reacted, and they produced exactly 2 molecules of hydrogen iodide. That's how a balanced chemical equation works. It locks those 3 things together. So we want to keep track of how much reaction is occurring, and this is the strategy that we're going to use over and over and over again. This particular problem-solving strategy, which we call an ICE table. All right, and our ICE table is this bookkeeping strategy that we use for these equilibrium problems. Okay, so I'm going to shrink this down a little bit so I got a little bit more room. Okay, so first when we build an ICE table, what we're going to do is we're going to make columns for all of our reactants and products. So this table is going to have columns for our reactants and products. And it's going to have 3 rows to it. which we're going to label I, C, and E. Okay, so for this example here, we're talking in terms of pressure. So I'm going to make this table where I have the pressure of my reactants and my product. Okay, so here are my columns in my ice table. All right, and then I'm going to have these 3 rows. One we're going to label I. The next we're going to label C. And the last one, E. Okay, so the I in our ice table is because this row here is where we're going to include the initial amount of our reactants and products. How much do we start out with before any reaction has occurred? The C is where we're going to keep track of the change in our reactant or product pressure as this reaction occurs. And then the E is going to be for our value at equilibrium. All right, so our rows are initial, change, and equilibrium. All right, so now we're going to fill out that I box, that I row. I again for initial. This is the initial either concentration or pressure, depending on what units you're using to talk about the amount of product and reactant. All right, we're going to pull that directly from the problem. So in this problem here, what should be my initial pressure of that hydrogen gas? 1.5. All right, I'm going to be good and put my units. What about my iodine gas? 2.3. And how much product do I have? Initially, when I throw this hydrogen and this iodine together in the flask, how much product is in there? None. I don't have any in there. You could start a reaction with some product in there if you really wanted, but typically you're combining reactants together to make your product, right? So we don't have any of that product in there yet. Okay? So now what about that change box? This is the change in our concentration or pressure. As that reaction proceeds towards equilibrium. And this is what we don't know. I don't know how much reaction has occurred, right? That's what I'm trying to figure out. So for this change box here, we're going to use a variable. And we're just going to pick everybody's favorite variable, x. All right? So in all of my change boxes here, what's going to appear is that variable x. I don't know how much change has occurred. All right, but we're not quite done. So importantly, in this reaction, what's going to happen to the pressure of my reactants as they combine together to form products? Is it going to go up or down? It's going to go down. And what's going to happen to the pressure of my product as it gets created? It's going to go up. So we got to put in the correct sign for these variables here. Reactants decrease in concentration or pressure, so they go down. And our products increase in their concentration, or in this case pressure, so they go up. All right, so in all your reactant boxes, you have a negative sign. In your product boxes, you have this positive sign. All right, so let's just note here we're going to use variable x. We're going to note that for reactants, use a negative sign, and for products, we're going to use a positive sign. All right, and then the last thing we got to do is, according to this balanced chemical equation, one molecule of hydrogen combines with one molecule of iodine to produce two molecules of that HI. All right, so that 1:1 to 2 ratio also has to be included in our change box. If we're going to use up X molecules of hydrogen and X molecules of iodine, that's necessarily going to create 2 X molecules of our product. All right, so we're going to use this variable X. For our reactants, we use a negative sign, and our products, we use a positive sign, and then we have to include those stoichiometric coefficients. All right, so in the I box goes our initial concentration or pressure, what we got when we mix these two things together initially. Our change box here is what we don't know, and that's when we're going to use this variable x. All right, we got to pay attention to the sign of that change box, as well as include any stoichiometric coefficients. So to be clear, this 2 in this change box comes from the fact that there was a coefficient of 2 in that balanced chemical equation. All right, and then the last one, our E box, which is for our concentration or pressure at equilibrium. All right, to fill out this E box, we're going to simply sum those first 2 rows. All right, so how you fill out the E box is you sum or add together the E and the C. I'm sorry, the I and the C. Okay, so for my equilibrium pressure of hydrogen gas, that's going to be my 1.5 minus X. My pressure of iodine is going to be my 2.3 minus X at equilibrium, right? My initial amount minus however much reactant. And then for my equilibrium box of HI, it's going to be 2x plus 0, or just 2x. Okay, so this is how we build our ice table here. Again, we got rows for, or rather columns for our reactants and products. And then we have this ICE row. The I is for our initial amounts. The C is for our change. So we use this variable X. Reactants are going to decrease. Products are going to increase. So we got to worry about the sign in that box, as well as making sure to include any stoichiometric coefficients. And then for the E box, you sum those first two rows together. All right? This is the same strategy we're going to use to build our ICE tables over and over again. What exactly we do with it from here might change from problem to problem. So we're going to see a few different uses of this ICE table. In this case here, if I continue reading, it tells me that at equilibrium, the pressure of that hydrogen gas is 0.25 atm. All right, which box on my ICE table corresponds to the pressure of hydrogen gas at equilibrium? My equilibrium box for hydrogen gas. So my expression here is that 1.5 minus x. All right, and I know that this has to equal 0.25 atm. So can we figure out what our change box is, what our value of x is? We're going to set these two equal to one another, right? I know 1.5 minus x has to equal 0.25 atm. This is what you all just did in your head quickly when you told me it was 1.25 atm that reacted, all right? But what we're going to do is we're going to take our pressure of H2 at equilibrium All right, we're going to take the pressure of H2 at equilibrium from our problem, and we're going to set it equal to the pressure of H2 at equilibrium from our ICE table. All right, so I want everybody to take a second, see if you can't do this. I'm going to give you a few minutes to do this on your own. I sort of set it up for you here, but I want to note that what I asked is what the pressure of that hydrogen iodine is at equilibrium, iodide. All right, so everybody take a second. See if you can't answer for me what the pressure of HI is at equilibrium. All right, and we look out here. I told you we were going to get to this portion of the course where the algebra gets a little bit too tricky to keep track of sig figs. We're there. All right, ICE tables, we're not going to try to keep track of our sig figs. All right, so if I rearrange this equation here, again, I have my pressure at equilibrium from my problem. I set it equal to my pressure at equilibrium from my ICE table. This allows me to solve for x by rearranging. That value of x is 1.25. All right, if I'm being good, what are the units on there? ATM. And I'm done. All right, you got to be careful here. Oftentimes with these ICE tables, you take a while, you're building your ICE table, you're going through this whole process, you're turning numbers into other numbers, your calculator spits something out, and you're like, okay, great, I'm done, all right? Make sure to go back and check the problem and what it's asking for, and check your ICE table. Because my problem is specifically asking me for the pressure of that hydrogen iodide at equilibrium. And which one of my boxes here corresponds to the pressure of hydrogen iodide at equilibrium? My pressure of hydrogen iodide at equilibrium is not x, but 2x. All right, so I know my value of X, but if I really want that pressure of HI, I'm going to have to solve by taking 2 times that value of X, or 2.5 ATM. Right? My value of X was 1.25. If I double that value of X, I get 2.5. All right, so now the last thing is that it asks me what the value of that equilibrium constant is, my Kp. Well, we built our Kp expression up here, but you can't just plug in any old pressure values that you want to an equilibrium expression. This is only going to work if you plug in the values at equilibrium. All right, but we know what our pressure is at equilibrium of our hydrogen gas. That was that orange box there. I know what the pressure is of my product at equilibrium. That's what we just calculated. So now if I can just plug in the pressure of my other reactant at equilibrium, I can get the value of that equilibrium constant. All right, so everybody take a second, calculate the value of that equilibrium constant. Let me just note here, as we said in our equilibrium expression, I am squaring that pressure of my product. So I'm going to have to square that 2.5 value when calculating my Kp here. All right? Whatever you plug in, whatever is in this box here, you have to plug that into your equilibrium expression and hit with any exponent that you have in that equilibrium expression. All right, my pressure of that hydrogen gas, that was given to me at equilibrium as 0.25 ATM. My pressure of my product, we calculated that at equilibrium to be 2.5 ATM. And now in order to get the pressure of that iodine at equilibrium, I need to do my pressure of iodine at equilibrium box, 2.3 minus X, which equals 1.05 ATM. Okay, that was really messy. And then I'm going to take these and plug them back into my equilibrium expression. Again, just kind of color coding here so we can see what values go where. I'm going to take that 2.5, I'm going to square it, divide it by 0.25 times 1.05, That's how I'll get my Kp. Oh, somehow my square disappeared. All right. And I get a value of, we're just going to take it to one decimal place here, 23.8. All right, and so what would I say about this particular reaction? Does it favor the products or the reactants? So this favors the products. Does it strongly or weakly favor the products? It only weakly favors our products. All right, so let's get another one here. What are we going to do? We'll take nitrogen again. I'm going to react it with fluorine. To produce nitrogen trifluoride. All right, so everybody's going to take a second and balance this chemical equation and give me a Kc expression here. All right, so we're going to do our products over our reactants. Now that we're at Kc, we're talking about concentration of our products over concentration of our reactants. All right, if we have a balanced chemical equation here, we see that we're going to turn that coefficient of 2 into an exponent for our product, and I'm going to have to cube that fluorine concentration. All right, and now I'm going to tell you that we're going to combine 3.3 molar fluorine gas and 1.4 molar nitrogen gas, and then at equilibrium, the concentration of that fluorine has decreased to 1.2 molar. All right, and I want to know what is the concentration of that product that we produced. All right, so everybody's going to take a second and set up our ice table here for this particular problem. sign that variable should be. We're going to make sure to include any coefficients in that change box as well. What's up? It did. It had a coefficient of 1.
Okay, yes.
Yes,
But now this one
correct.
has-
So now this is going to have a coefficient of 1 in this change box, and this is going to have a coefficient of 3 in that change box. Right? Those ratios of 1 to 3 are locked together here. Okay, just to fill this in pretty quickly here, all right, I'm going to have a value of 3.3, nope. I'm going to have a value of 1.4 molar for my concentration of nitrogen, and 3.3 molar for my concentration of fluorine. I don't have any product in there. For our change box, we're always going to use that variable x. All right, we got to figure out what our sign is. All right, our sign depends on whether we're talking about a reactant or a product. So in this case here, my reactants are my nitrogen and my fluorine, right, on this side. So these are going to decrease in concentration, whereas my product's going to increase in concentration. And according to my balanced chemical equation, for every 1 nitrogen molecule that's consumed, 3 fluorines are consumed, and that produces 2 of these products. So I'm going to include those coefficients as well. I should have a 1, or I can just leave it, in my nitrogen box, a 3 in my coefficient for my fluorine, and 2 for my coefficient of my product. All right, and then for our last box here, we're going to sum up the I and the C. So this will be 1.4 minus x. This will be 3.3 minus 3x. And this will be 0 plus 2x, or just 2x. All right, now what I know, how I'm going to go about solving this problem, solving for that variable x, is what's given to me is the fact that my fluorine concentration at equilibrium is 1.2 molar. So my fluorine concentration at equilibrium is this box here. Whoops. And I know that this must be equal to 1.2 molar. So I'm going to set that 1.2 equal to 3.3 minus 3x. I'm going to rearrange this equation here to solve for x. And I get x is a value of 0.7 molar. All right, 3.3 minus 1.2. Take that and divide it by 3 to get my value of x. All right, and then to finish this problem off, what I wanted to know is what the concentration of my product is at equilibrium. So it's not going to be x, but rather 2x, or a concentration of NF3, again, equal to 2x, or equal to 1.4 molar. Well, all right. I could have also asked you for that value of that Kc. I could have asked you for the equilibrium concentration of nitrogen as well. Right now we can fill in this entire table because we were able to solve for that value for x. Cool. All right, we will finish off. This is a pretty quick chapter. We will finish this off, no problem, next time. Yeah.
So I understand in the size table,
Yeah.
in both here we added like 2 in front of the x, right?
Okay, so the 2 up here.
So 2 up here, but whenever we do the equation like here, but then we initially exponent to 2.
That's,
like,
yeah, so it appears in 2 places. It appears both as another, just like a coefficient in your change box, and then it appears as an exponent in your equilibrium expression. It's going to appear in both places. What's up? Okay, send me an email about it. I'll take a look at my analysis. How's it going? Nice, awesome.
I sent you content for tomorrow's
Okay.
session. Just take
I'll take a look at it.
Yeah, definitely.
I'll do it real quick before I leave. How's it going? So Tuesday, if you can make it, will be just a review session. There won't be a daily quiz, and if you need to, you can use that time to take your exam. There won't be anything new. And yeah, again, if you can't make it, it's not a big deal. I don't take attendance on those days.
Sounds good. Thank you.
I have a question about the algebra part.
Okay.
I don't know if I tried to do it out on paper, but I got like negative 1.4 and you got 0.7.
All right, so 3.3 minus 3x equals, what was it, 1.2?
1.2.
1.2. All right, we need to get x all by itself. So we're going to add the 3x to both sides. And then I'm going to subtract the 1.2. So this is 3.3 minus 1.2 equals 3x. All right, if I do this subtraction here, this is 2.1 is 3x. So divide both sides by 3. That's how I get that 0.7 equals x.
Okay, I think I was subtracting the 3.3.
You can, and then you're just going to need to divide by negative 3 at the end, since that's what you're left with over here. Yeah, so you could do negative 3x equals 1.2 minus 3.3, and then to get x, you're going to take all this and divide it by negative 3. That would work too.
Okay, that makes sense. Thank you.
Yep. How's it going?
Yeah, a couple times and you've been really helpful. So
Oh,
I wanted
yeah,
to
okay,
ask
cool,
you
yeah.
about this one question. I have a screenshot of it, but I missed it a couple times and I lost a lot of points because I wasn't really sure what it was asking. So I was wondering if you could clarify like the.
Yeah, so this was a bad one. It really should have been more clear about looking for the mass of the solvent, not the solution.
Okay.
All right, so yeah,
Yeah,
so
because I was
this.
doing massive solvent plus massive solute.
Yeah, so massive solute though, were you using a molar mass and everything?
Because they gave you this, yeah. So I
Okay,
had to
so you were going along. Okay, yeah, and you could do that. That would work. But no, you're right. That was a poorly worded question. So I actually already sort of changed it around to clarify. I was hoping to get people before the end of the week, but you clearly did it nice and early. Just send me an email about it. I'll
Okay,
give you your
sounds
points.
good. Thank you.
Yep. How's it going?
Good, how are you?
Good.
I was just wondering what the best way to study for your test is. I know you mentioned redoing the homework, but
Yeah.
like, are there other things you recommend?
So I mean that's pretty much it. So there's the study guide as well. So you can
Yeah.
treat that like a checklist to make sure that you like, okay, yep, I got that, don't remember that, need to go back and do that. There are some like keywords in there that are highlighted. You want to make sure you know your definitions of and stuff like that. But yeah, generally speaking, just practice problems. You can just use your past homework assignments.
Okay. And is your test multiple choice or?
It is multiple choice.
Okay,
How many
completely?
questions?
It is, yep. I don't know. That question drives me nuts. One, I don't really know off the top of my head. Two, I don't know what you do with that information. Whatever
Just to
number you need
expect.
to hear, it's that number.
How to maintain your time.
Yeah.
Well, certainly that is going to be a quick calculation that you're going to do. But I mean, you don't know the difference between like, some questions have multiple parts.
Yeah.
It's timed.